If I asked you to differentiate the product of two functions f of x and g of x, you would follow the product rule for differentiation. For example, x cubed minus 3 multiplied by x minus e to the x. First, we take the derivative of x cubed minus 3 multiplied by x minus e to the x plus x cubed minus 3 times the derivative of x minus e to the x. We then evaluate the derivatives to yield the answer. Thus, for indefinite integrals, we can rewrite this as or this equation is called the formula for integration by parts and is often rewritten as the integral of u dv is equal to uv minus the integral of v du, where u is equal to f of x, v is equal to g of x, du is equal to f prime of x, and dv is equal to g prime of x. Now that we have a formula for integration by parts, let's try it out on an example. The indefinite integral of the natural logarithm of x. The first step is we need to identify u, du, v, and dv. For this problem, the best choice would be to set u to be the natural logarithm of x, because we know that the derivative is dx over x. If that's u, then dv must be dx, and thus v is x. Plugging these into the formula, we can solve it. It's equal to x times the natural log of x minus the integral, and now it's v du, so v is x, du is dx over x. Those x's now cancel, and we're left with x, the natural log of x, minus the integral of dx, which is now equal to x, the natural log of x, minus x plus a constant. Let's try another example. The indefinite integral of x times cos of x. Instead, let's use f, f prime, g, and g prime. For this problem, we'll use f is equal to x. That way, f prime is dx. G prime is then cos of x, dx, and g is sine x. Plugging these into the formula, we get x times sine of x minus the integral sine x dx, which gives us x sine x minus cos of x plus a constant. Now let's try and do the same problem again, but instead let's pick a different f prime, g, and g prime, and let's see what happens. So the first one we did, f is equal to x, so let's say f is equal to cos x, and g prime is x dx. Well, f prime is minus sine x dx, and g is 1/2 x squared. Putting this into the formula, we get 1/2 x squared cos x minus the integral 1/2 x squared minus sine x dx, or now compare this to this. By choosing the correct f and g, we have reduced the integral to something that was easier to solve. So for example, in this integral we had x times cos x, but in this integral we had sine x. But if we choose the wrong ones, we ended up with something even more complicated, x squared sine x. So we have to be careful about what we choose. Our goal then is to determine what f and g should be so as to make the integral simpler and easier to solve. Now so far we have only solved indefinite integrals. But if we apply part of the fundamental theorem of calculus to the formula for integration by parts, we can now solve definite integrals. The formula we use looks like this. Here we evaluate f and g from a to b. Let's try this problem. So for this problem, I'm going to choose the inverse sine to be my f, and f prime is 1 over the square root of 1 minus x squared. By choosing that, I can set g prime to be dx and g to be x. Following this formula, this definite integral is equal to x sine inverse of x evaluated from 0 to 1/2 minus the integral from 0 to 1/2 of x over the square root of 1 minus x squared dx. The next thing to do here is to use u substitution. If we let u equal to 1 minus x squared, then du is equal to minus 2x dx, or x dx is equal to minus 1/2 du. If we're going to apply u substitution, we then have to change the bounds. When x equals 0, u will equal 1. We can see it with this equation. When x is equal to 1/2, u is equal to 1 minus 1/2 squared, which is going to be 1/4. 1 minus 1/4, or 4 quarters minus 1/4, is 3/4. So this equals x sine inverse of x evaluated from 0 to 1/2 minus 1/2 the integral from 1 to 3/4 minus du over u to the 1/2, which equals x sine inverse x evaluated from 0 to 1/2 plus 1/2 times u to the power of 1/2 divided by 1/2 evaluated from 1 to 3/4. Square root of 3/4 minus 1. This is 0. Now with this, we can use a triangle. (30°, 60°. This will be 1, square root 3, and 2. And we can see that the inverse sine of 1/2, opposite over hypotenuse, is 30°, or pi over 6. So we have 1/2 pi over 6 plus square root 3/4 minus 1. Plus the square root of 3/4 minus 1. Earlier in the video, I stressed that it was important to be careful about which function you assigned to u or v, because choosing the wrong function can lead to an integral that's more complicated than the one you had started out. You are trying to determine which way to go about it so that you simplify the problem. There is a rule of thumb you can use to help you. This is the acronym for it, and it stands for logarithm So these are logarithmic functions, like the natural log or log to a different base. The inverse, trig, or hyperbolic, like arc, cos or arc like cos inverse of x or cos h inverse of x. A for algebraic. Such as x squared or x to the 5. T for trig. And this includes hyperbolic, like sinh. And E for exponential. Now this rule of thumb is what you use for determining what your u function will be. You're given a problem of the form u dv, and you want to apply the formula for integration by parts. You want to look at the integral and determine what you want to use for your u. And this rule of thumb will help you determine that. So for example, if we had an integral that had a logarithmic function and an algebraic function, then we would pick the logarithmic function to be our u. In a previous example, we solved this integral. But suppose you weren't sure of your answer. Here's how you could check it. You simply take the derivative. So we apply the product rule, the derivative of x, sine of x plus x times the derivative of sine x with respect to x plus the derivative of cos x with respect to x, and the derivative of a constant with respect to x, which is of course 0. So we have sine x plus x cos x plus, and the derivative of cos x is minus sine x, which we can see cancels with this, and we're left with x cos x. And there we go. That's how you can check. So for our last example, we are going to prove this formula. To start, what we need to do is rewrite the integral cosine nx dx as cosine n minus 1x cos x dx. We will let u equal cos n minus 1 x. Du is n minus 1 cos n minus 2 x minus sine x dx. So this follows from the generalized power rule. dv is cos x dx, so v is sine x. So this equals sine x cos n minus 1x minus n minus 1, the integral, cosine n minus 2 x. Now it was a minus sign, so that becomes a plus. Sine squared x dx. Next thing to notice is that we have an n minus 2 here and a sine squared here. So it would be nice if this sine squared x was actually a cosine. So to make that happen, we can use the identity Now this is all equal to the integral of cos to the power of n x dx. So they cancel, and this is a negative, and we can bring it over here. So we have n times the integral cos to the power of n x dx equal to all of this. The next step then is just to divide by n. And this looks like this. So there we go. Q.E.D.